OSPF, aka Open Shortest Path First. What is OSPF? OSPF, which is also known as Open Shortest Path First, is a robust link state interior gateway protocol, or IGP. It is one of the most widely used IGPs. It tends to get used in larger networks when it is discovered that RIP, Routing Information Protocol, isn't going to work, or they are looking for very fast convergence. Some OSPF terminology. Router ID. In OSPF, there is a unique 32-bit number assigned to each router. This is chosen as the highest IP address on the router. Neighbor routers. Two routers with a common link that can talk to each other. Adjacency. A two-way relationship between two neighbor routers. Neighbors don't always form these. LSA is a link state advertisement are flooded. They describe routes within a given link. Hello protocol. This is how routers on a network determine their neighbors and form LSAs. Area, a hierarchy. A set of routers that exchanges LSAs with others in the same area. Areas limit LSAs and encourage aggregate routes. How does it work? OSPF is a link state routing protocol that you think of as a distributed map. To get this information distributed, OSPF collects connectivity information from all of these devices on the network, and then stores all of this information in a database and uses that information to build a topology map. This information allows OSPF to identify the best or shortest route to every other network segment. This route selection is based on overall hops to the destination as well as link speed or link cost. It not only finds the best route, but sometimes it will, when possible, make a candidate or backup route to the destination if for whatever reason there is a transmission failure. Once it creates its topology map, OSPF populates the routing table with the chosen routes to each destination. As traffic passes from router to router, each router evaluates the best path to the destination in the network. In some cases, the process can lead to routing loops on the network because each one is evaluating the path based on its own link state database. OSPF typically will use multicast to share connection information with its neighbors, and this information is sent to the multicast address. OSPF has two main versions right now, version 2 and version 3. Version 3 supports IPv6, but other than that, no major technical differences exist between the two versions. Routing example. A quick and dirty example of OSPF would be to take a look at this diagram and say that assuming all links have the same cost, what would be the fastest way for R1 to connect to R5, or for R3 to connect to R5? First one is a little tricky because you could go from R1 to R2 to R5, or you could go R1 to R4 to R5. But the second one, the R3 to R4 R5, is a much more simple route. Enabling OSPF on the router. Enabling OSPF on a router is very similar to a lot of the commands and steps we use for other items in the class, like setting up RIP and even setting up DHCP. We need to enable it in configuration mode, then use a command to enable it. Enabling an OSPF process using the router OSPF process ID command. Assigning areas to the interface using the network or IP address mask area ID command. The OSPF process ID is a numeric value local to the router. It doesn't have to match process IDs on other routers. The network command is a way of assigning an interface to a certain area. The mask is used as a shortcut and it helps putting a list of interfaces in the same area with one-line configuration lines. The mask contains wildcard bits where 0 is a match and 1 is a do not care bit. The area ID is the area number we want the interface to be on. The area ID can be an integer between 0 and 4,294,967,295, or it can take a similar form to an IP address as a.b.c.d. The algorithm. To determine the shortest path first, OSPF uses an algorithm to determine what and how to transmit its data. The shortest path is calculated with the use of the algorithm. It's a complex algorithm, but here's a simple way of looking at it. Upon initialization or due to any change in routing information, a router generates a link state advertisement. This advertisement represents the collection of all link states on that router. All routers exchange link states by means of flooding. Each router that receives a link state update should store a copy in its link state database and then propagate the update to other routers. Number 3. After the database of each router is completed, the router calculates the shortest path tree to all destinations. The router uses the Dijkstra algorithm in order to calculate the shortest path tree, the destinations, the associated costs, and the next hop to reach those destinations from the IP routing tables. In case no changes in the OPSF network occur, such as cost of a link or a network being added or deleted, OSPF should be very quiet. Any changes that occur are communicated through link state packets in the Dijkstra algorithm is recalculated in order to find the shortest path. OSPF cost. The cost, also called the metric of the interfaces in OSPF, is an indication of the overhead required to send packets across a certain interface. The cost is inversely proportional to the bandwidth of that interface. A higher bandwidth is a lower cost. There is a formula to calculate the cost below. Like most things, the cost is set by default, which is calculated by the bandwidth, but you can use the IPOSPF cost value command to force the cost of an interface in subconfiguration mode. We mentioned earlier that OSPF uses flooding to send the link state updates between routers. Any change in routing information is flooded to all routers in the network. Areas are introduced to put a boundary on the explosion of link state updates. The calculation of the Dijkstra algorithm and the flooding are limited to changes within one area. All routers within an area have the exact link state database. Routers that belong to multiple areas and connect these areas to the backbone area are called area border routers. ABRs must therefore maintain information describing the backbone areas and other attached areas. An area is an interface specific, and with that being said, a router that has all of its interfaces in the same area is called an internal router, and a router with interface across multiple areas is called ABR. We also have routers that act as gateways for redistribution between OSPF and other routing protocols, RIP and BGP in the case of this picture below. When multiple areas are in use, OSPF has some special restrictions. If more than one area is configured, one of these areas has to be area 0. This is called the backbone. When designing networks, it is good practice to start with area 0 and expand into other areas later on. The backbone has to be at the center of all areas, which means that all areas have to be physically connected to the backbone. The reasoning behind this is that OSPF expects all areas to inject routing information into the backbone, and in turn the backbone will send that information into other areas. The diagram shows the flow of information in an OSPF network. All areas are connected to the backbone. In some rare situations where a new area cannot have a physical access to the backbone, a virtual link can be used. Virtual links are used for two purposes: linking an area that does not have physical connection to the backbone, and number 2, patching the backbone in case discontinuity of area 0 occurs. Link state packets. There are different kinds of link state packets, but these are the ones you might normally see in an OSPF database. Router links. Describe the state and cost of the router's links interfaces to the area. Number 2, summary links. Originated by ABRs only. Describe networks in the AS but outside of an area. Also describe the location of the ASBR. Number 3, network links. Originated from multi-access segments with more than one attached router. Describe all routers attached to a specific segment. Originated by a designated router. External links. Originated by an ASBR. Describe destinations external the autonomous system or a default route to the outside AS. As noted above, router links are an indication of the state of the interfaces on a router belonging to a certain area. Each router will generate a router link for all of its interfaces. Howdy neighbors. Routers that share a common segment become neighbors on that segment. Neighbors are figured out by something called the Hello Protocol. This really makes me want to say Hello Kitty Protocol, but that might be too far. Hello packets are sent periodically out of each interface using IP multicast. Routers become neighbors as soon as they see themselves listed in the neighbor's hello packet. This means you will always get a two-way communication. Neighbors negotiation applies to the primary address only. Secondary addresses can be configured on an interface with the restriction that they have to belong to the same area as the primary address. Two routers have to agree on the following to become neighbors. Area ID. The two routers having a common segment, their interfaces have to belong to the same area on that segment. Authentication. Ospf allows for the configuration of a password for a specific area. Routers that want to become neighbors have to exchange the same password on a particular segment. Hello and dead intervals. Ospf exchanges hello packets on each segment. This is a form of keep alive used by the routers in order to acknowledge their existence on a segment. And finally, stub area flag. Two routers have to also agree on the stub area flag and the hello packet in order to become neighbors. Adjacencies. Adjacency is the next step in the neighboring process. Adjacent routers go beyond the simple hello exchange and proceed into the database exchange process. To minimize the amount of information exchanged on a particular segment, Ospf elects a designated router and one router as the backup. The DR and BDR election is done via the hello protocol. Packets are exchanged via IP multicast on each segment. The router with the highest Ospf priority on a segment will become the DR for that segment. The same process is repeated for the BDR. In case of a tie, the router with the highest RID will win. The adjacency building process takes effect after multiple stages have been fulfilled. Routers that become adjacent will have the exact link state databases. Router interfaces will go through different states before becoming adjacent to another router. Those are listed below. Down. No information has been received. Attempt. Every effort should be made to contact the neighbor. Init. The interfaces has detected a hello packet. Two-way. There is bidirectional communication between neighbors. Xstart. Routers are trying to establish the initial sequence number that is going to be used in the information exchange of packets. Exchange. Routers will describe their entire link state database by sending database description packets. Loading. Routers are finalizing the information exchange in full. At this state, the adjacency is complete. To check an interface status, you can use the show IP ospf interface command. And that is what I have on OSPF, guys. This is brought to you by Kevin Harvey. Thank you, guys.